Okay, so I want to talk about this theorem here, which says that if you have a nested sequence of closed, bounded, non-empty sets, then the intersection is a closed, bounded, non-empty set too. Okay, so the first thing is let's provide some clarity around what it means to be a decreasing sequence of sets. And so here, when we say decreasing, we mean that suppose here's F1 and then F2, right, and then F3, so forth and so on. So Fn is a subset of F sub n minus 1. Okay, this is true for all n. Okay, so the first thing I want to do is I want to explain and just show you an example of why we need to assume that our sets are closed. And here's how I'm going to show you. I'm going to show you by giving you an example where this does not happen and our sets are not going to be closed. So we'll have a decreasing sequence of bounded non-empty sets, but their intersection is not bounded and non-empty. Okay, so just suppose here we are, k is equal to 1. So we're working with just r. And I want f1, I want it to be 0, 1. f2, I want it to be 0, 1 half. Right? So fn, I want to be 0, comma 1 over n. So here's 0, here's 1. So like here's f1, f2 is here, f3 is here, f4 is here. They're definitely nested, right? They're decreasing sequence. Each fn is non-bounded. So for every n, fn is bounded, non-empty, right? And in fact, for us, each set is open. But what is the intersection? So the intersection of all these fn's is the empty set, right? So just because you have a nested sequence of sets or nested sequence, decreasing sequence of sets, you can have a decreasing sequence of sets.
It's 10:30.
Thank you. Each of the sets is non-empty, but that doesn't guarantee that the intersection is also going to be non-empty. Okay. There's nothing special about these sets being open. We could change these to be sets that are not open. So suppose that's F1, that's F2, and then, 1/3 could be F3. So we could have it so that each Fn, this is a set that's not open and it is not closed, right? So it's not open and not closed. So that's a key fact to recognize, that you can have a set that is open and closed. You can have a set that is open but it's not closed. You can have a set that is closed but it's not open. And you can have a set that is not closed and it's not open. Okay? So here we've got some sets that are nested, decreasing, non-empty, but their intersection is still going to be empty. So it is key, in order for us to know and be guaranteed to have the intersection non-empty, we need to know that each set is closed. Okay, so let's get into the actual proof of this. Okay, so we'll just do, for the sake of time, we'll just do a sketch of the proof. So first we want to show that F is bounded. Well, now F is bounded That's easy because F has to be a subset of F1, right? And F1 is bounded. Okay. What about the fact that F is closed? Well, F is closed. Let's see here. Remember that F is closed if and only if its complement is open, right? Now, what is its complement? Its complement is going to be the intersection of these sets, the complement of the intersection. So we want these to be open. But what is the complement of the intersection? It is the union of the complements, right? And remember, we said that since each Fn is closed, well, so remember we said that union of open sets is open. So since each Fn is closed, each Fn complement is open. Therefore, the union of the Fn complements also must be open, right? Because union of open sets is open. Okay, so since that union is open, that means that F itself is closed. So the last thing, so we've got that it's closed, we've got that it is bounded. Last thing we need to explain is, and prove actually, is we need to prove that it is non-empty. That when you take this intersection, these intersections, you get something that's non-empty. Okay, so here's what we're going to do. Picture-wise, we've got F1, and now here's F2, F3, right? And so forth and so on. So to get that our intersection is non-empty, what we're going to do is we're going to show that there's a sequence. Here's how we're going to pick our sequence. Pick some point in each Fn, right? So for each n, since Fn is non-empty, there exists some x, we'll call it xn, in Fn. Now we've got a sequence. This is a sequence in, this is a sequence, believe it or not, this is a sequence in F1, right? Because our sets are nested, xn is a sequence in F1. F1 is bounded, and by Bolzano-Weierstrass, every bounded sequence contains a convergent subsequence. So there's some x in k, right? So now this x in k is a convergent subsequence. And it's going to converge to some limit, and suppose it converges to x naught. It's a convergent subsequence in F1. Say its limit is x naught. So our claim is that x naught is in F. So what we're trying to say is that x naught is in the intersection. And how do we prove that? We prove that by showing that we need to show that for every n, x naught belongs to Fn, right? But now, here's how we do that. So fix n. Then at some point, right? So at some point, so here's our Fn. At some point, this sequence x n k, since it's a subsequence, at some point, one of these nks has to be bigger than n, right? So go down far enough in your subsequence to where now the rest of right? The rest of this sequence, subsequence, is inside of Fn, okay? Fn is closed. Well, let me not say that. Okay, so we now have we can create a subsequence of this subsequence, and it's basically just the tail end of it. So look at, right, so suppose this is whatever point at whatever term the nk gets bigger than n, all of the rest of those terms are going to be within Fn, right? And that is also going to be that will still be a convergent sequence, and it will converge to the same limit as the original subsequence. So it's still going to converge to x naught, right? So x naught has to belong to, x naught has to belong to Fn, right? Because x naught is the limit of a convergent sequence. And we have a proposition, which is proposition 13.9, which tells us that a set is closed if and only if it contains the limit of every convergent sequence of points in the set, right? So since Fn is closed, it will contain the limits of all of its sequences. And so we'll have the tail end of this sequence here has to be in Fn. And since it's convergent, its limit also has to be in this set Fn. So we've shown that for any n, x naught is actually an element of Fn. So x naught is in the intersection of all Fn's. Okay, so that means that the intersection is non-empty.